The moon's surface composition and geological features are distinct from Earth. Lunar geology includes layers beneath the surface, similar to Earth's structure. Unlike Earth, the moon lacks active tectonic plates. This absence influences the moon's geological activity and surface characteristics. The explosive yield refers to the amount of energy released when a bomb detonates. This energy release is typically measured in terms of equivalent mass of TNT, trinitrotoluene. The potential energy release depends on the type and amount of explosive material used. Detonation on the moon's surface would have different effects compared to Earth due to the lack of atmosphere. Factors such as crater size and seismic waves would be key indicators of the explosive yield. The simulation depicts an initial explosion on the moon's surface. This explosion results in the immediate formation of a crater. The force of the explosion causes the ejection of lunar material. Ejected material includes dust, rocks, and other surface debris. The simulation visualizes the dynamic effects of such an impact event. Shockwaves propagate through the moon's crust and mantle following impacts or internal events. These waves are analyzed to understand the moon's internal structure and composition. Seismic activity on the moon is influenced by these shockwave interactions. Monitoring shockwave patterns helps in predicting and understanding lunar seismic events. Data from seismic sensors on the moon provides insights into the depth and intensity of shockwaves. Analysis contributes to a comprehensive understanding of lunar dynamics and geological processes. An explosion on the moon could impart a significant force, altering its rotational speed. Changes in the moon's rotation could affect its overall stability. The explosion's force could also introduce perturbations to the moon's orbit around Earth. These orbital changes might affect the moon's distance from Earth. Such alterations could have long-term consequences for tidal patterns on Earth. This simulation visualizes the moon's orbital path following a hypothetical explosion. The explosion introduces potential deviations from the moon's original trajectory. These deviations are calculated based on the force and direction of the explosion. The simulation models the moon's altered path, showing its new orbital parameters. An explosion creates a debris field composed of ejected fragments. Analyzing the debris field involves examining the size distribution of the fragments. Fragment size can range from microscopic particles to large chunks of material. The velocity of ejected fragments is another key parameter to measure. Fragment velocity indicates the force and direction of the explosion. Together, size and velocity help reconstruct the explosion event. This simulation visualizes the trajectory of lunar debris in space. The simulation focuses on the path and movement of fragments originating from the moon. It explores the possibility of some lunar debris entering Earth's atmosphere. The simulation models the gravitational forces influencing the debris's trajectory. Various factors, such as initial velocity and solar radiation pressure, are considered. The simulation helps scientists understand the potential risks associated with lunar debris. Lunar debris consists of fragments ejected from the moon due to impacts from asteroids or meteoroids. These fragments can vary in size, ranging from microscopic dust particles to larger rocks. Earth's gravitational pull can draw this lunar debris into its atmosphere. As the debris enters the atmosphere, it heats up due to friction, creating visible streaks of light known as meteors. A large number of meteors appearing in a short period is called a meteor shower. Larger pieces of lunar debris that survive atmospheric entry can impact the Earth's surface. This analysis focuses on the potential effects of large lunar fragments colliding with Earth. The primary consequence of such impacts is the formation of impact craters on Earth's surface. The size of the crater would depend on the size and velocity of the lunar fragment. Larger fragments could create extensive regional damage upon impact. This damage could include seismic activity, atmospheric disturbances, and widespread destruction. The severity of the impact would depend on the fragment's composition and angle of entry. The moon's surface environment is susceptible to alterations from explosions. Explosions on the moon can cause significant redistribution of surface debris. This redistribution can lead to long-term changes in the lunar surface composition. The extent of these changes depends on the magnitude and location of the explosion. Understanding these impacts is crucial for planning future lunar activities. Explosions on the moon can create debris fields, posing risks to future lunar missions. Ejected material can travel considerable distances, impacting spacecraft and habitats. Lunar dust stirred up by explosions can interfere with sensitive scientific equipment. Contamination from explosion byproducts may compromise the integrity of lunar samples and research sites. An explosion on the moon carries the potential to disrupt existing lunar resources. It may also damage or destroy any infrastructure present on the lunar surface. Assessing the potential impact is crucial for lunar mission planning. Understanding the risks helps in developing mitigation strategies. An explosion could potentially affect Earth's tides. Changes in gravitational forces could disrupt tidal patterns. Altered tides may lead to shifts in coastal water levels. These shifts can impact the distribution of marine habitats, resulting in changes to coastal ecosystems and biodiversity. An explosion in space could potentially disrupt Earth's communication systems. This disruption may extend to satellites orbiting the Earth. Satellites play a crucial role in global communication networks. The explosion could also interfere with radio wave transmissions. Radio waves are essential for various communication technologies. Therefore, the integrity of both satellites and radio waves is vital for maintaining communication infrastructure. The explosion's potential impact on Earth's magnetic field is being analyzed. This analysis focuses on the possibility of disruptions to navigation systems. Such disruptions could stem from alterations in the magnetic field's stability. Changes in the magnetic field can affect the accuracy of magnetic compasses. Navigation systems relying on magnetic field data may experience errors. Explosions in space have the potential to affect Earth's climate. These effects could lead to alterations in global temperatures. Changes in temperature can disrupt established weather patterns. These disruptions may manifest as extreme weather events. The severity of the impact depends on the magnitude and proximity of the explosion. Further research is needed to fully understand these complex interactions. An explosion could potentially disrupt Earth's ecosystem. This disruption could lead to significant imbalances in natural processes. Such imbalances can threaten the survival of various species. The ultimate consequence might be species extinction. Therefore, the explosion poses a severe risk to Earth's biodiversity. The analysis focuses on assessing the potential impact of an explosion on Earth's human population. A key consideration is the possibility of displacement of communities. This displacement could lead to significant migration patterns. The analysis aims to understand the scale and consequences of such population movements. An explosion could potentially disrupt Earth's economy. This disruption may lead to financial instability. Economic systems are vulnerable to large-scale unexpected events. Financial instability can manifest in various forms. These forms include market crashes and currency devaluation. The severity depends on the scale and nature of the explosion. A major explosion could destabilize Earth's political systems. This destabilization may stem from resource scarcity or infrastructure damage. The disruption could lead to increased tensions between nations. Escalating tensions might result in conflict and potentially war. An explosion in space could potentially affect Earth. This impact may extend to Earth's cultural heritage. Earth's cultural heritage encompasses a wide range of historical sites. These sites are physical representations of human history and cultural achievements. The explosion could lead to damage or destruction of these sites. Consequently, this could result in the loss of invaluable historical and cultural information. An explosion could potentially disrupt scientific research on Earth. Such a disruption may lead to the loss of critical data. The loss of data can significantly hinder ongoing research projects. This could also result in the loss of accumulated knowledge. The overall impact is a setback for scientific advancement and understanding. An explosion could significantly disrupt Earth's ongoing space exploration efforts. The disruption may stem from damage to spacecraft or ground infrastructure. Safety concerns following an explosion could lead to a re-evaluation of mission protocols. Increased risks might necessitate the postponement or complete cancellation of planned missions. This could severely impact scientific research, resource acquisition, and future space development. Bombing the moon carries numerous potential consequences. Such actions could disrupt the lunar environment. Preserving the moon's environment is critically important. Protecting the lunar environment should be prioritized.